I am going to talk about discrete time, complex exponential and sinusoidal signals. As in continuous time, an important signal in discrete time is the complex exponential signal or sequence, which is defined by x of n is equal to c times alpha to the n. Okay, where x of n is the complex exponential. Signal, or it is also called sequence. Either you can call by signal or sequence in discrete time, but predominantly people will always call it as a sequence. Okay, where this c excuse me, c and alpha are in general complex numbers. Okay, so this could alternatively be expressed in the form like x of n is equal to c times e to the beta times n, where alpha is defined as e to the beta. Although the form of the discrete time complex exponential sequence given in this form, let me call 1 and this is 2, is more analogous. This is analogous to the form of continuous time exponentials like x of t is equal to a bar times e to the st. It is more often convenient to express the discrete time complex exponential sequence in this form, in form 1. Okay, now let us talk about real exponential signals. Okay, now the general form of complex exponential signal is c times alpha to the n. Now what we do, we consider c is equal to some real number. It can be any value, it can be 1 or 2 or whatever it is. It can be real number or and this alpha is also real, not necessarily integer. Be integer valued. Okay, only n has to be integer valued, it cannot take real values. So this point you should remember, c can take any real value and alpha also can take any value. Okay, now let us consider different cases if c and alpha are real. Okay, so we can have one of several types of behavior. Let us take case 1. So for all these cases I assumed c is real and alpha also real. Okay. Now for the first case, let us assume mod of alpha is greater than 1. Okay, in this case the magnitude of the signal grows exponentially with the n. Let us take one simple example and we will see how the magnitude grows exponentially. X of n is equal to c times alpha to the n. This is a general form. Now c is real. Let us assume c equal to 1 without loss of generality, and alpha is greater than 1. That's what we assumed here. So let's take alpha is equal to 2. Now what happens if substitute n is equal to 0, then x of 0 is equal to 1 times 2 to the power 0, which is 1. Substitute n is equal to 2, then x of 2 again is equal to 1 times 2 to the power 2, which is 4. N is equal to 3. Then x of 3 is equal to 2 power 3, that is 8, and so on and so forth. So if you plot the signal, then let's say this point is n equal to 0, 1, 2, 3, 4, 5, like that. When n equal to 1, so this is a magnitude, let's say 1. This is my x of n. And then when n is equal to 1, then you'll get 2. When 2, you'll get 4. When 3, it goes to 8. 2, 3, 4, 5, 6, 7. I don't have space here. It goes 8 like this. So if you look at this sequence, then it grows exponentially. Okay. Therefore, when alpha is greater than 1, it grows exponentially. Now consider the case mod of alpha. Second case, this is mod of alpha is less than 1. So in this case, what will happen? Let's say alpha is equal to 0.5, just for the simplicity. And again assume c is equal to 1. C can take any value, doesn't matter. Without loss of generality, let us assume c equal to 1. C is equal to 1. So x of n is equal to c times alpha to the n, that is alpha to the n, which is alpha value is 0.5 to the n. Now substitute different values of n. N equal to 0, then x of 0 is equal to 1. N, if we substitute n equals 2, then x of 2 is equal to 0.5 times to the 2, which is 0.25. Substitute n equals 3. X of 3 is equal to 0.5 times 0.5 to the 3. This is, I think, 0.125. Therefore, look at the values are decreasing as n increases. The values are decreasing. But here the values are increasing here. Initially, I had 2 here. Then I got 4. Then I got 8. Maybe afterwards, if I substitute n equal to 4, then I will get a 16, and so on and so forth. But here the values are diminishing here, for the case where alpha is less than 1. Now let us plot, let's say x of n. Now when n equals 1, when n equals 0, the value is 1. When n equals 1, I did not do that. When n equals 1, x of 1 is equal to 0.5. So it is 0.5, and then 0.25, 0.125. So maybe see, this is 0.125, this is 0.25, this is 0.5, and this is 1. Therefore, the sequence is decreasing. So this is called a decaying exponential. Now what about the negative values of n in this case? Suppose substitute if s equal, n equals minus 1, then x of minus 1 is equal to 0.5 to the minus 1, that is 1 by 0.5. What is 1 by 0.5? 2. Therefore, at minus 1, the magnitude is 2. Substitute n equals minus 2, then what will happen? X of minus 2 is equal to 0.5 to the minus 2, that is 1 by 0.5 whole square. 1 by 0.5 whole square is 1 by 0.25, that is 4. So therefore, at minus 2, when n equals minus 2, it goes up to 4. So like that for n equals minus 3, then it increases to 4, 5, 6, 7, 8. So in the when t is less than 0, then it is coming like this. So this is 4 and this is 2 and this one is 8, like that. So this is the decaying exponential. Decaying exponential when mod of alpha is less than 1. Similarly, in this case also you can plot. See here, when n is equal to minus 1, then x of minus 1 is equal to 2 to the minus 1. 2 to the minus 1 is 1 by 2. 1 by 2 is 0.5. Therefore, at minus 1, you have the value of 0.5. When n, if you substitute n is equal to minus 2, then you'll get this is 0.5 and maybe, okay, so this is 0.5 and this one is 0.25 and so on and so forth. So in the negative side it is like this, and this one is growing exponential, real exponential. Okay, so that's it. So that's it about real exponentials. Let me consider one more case to complete this. Now these two cases, let me show you through a figure. Insert, then pictures. In this, where is it? Yeah, it is this one. Now look at here, the growing exponential, it grows like that. Okay, where in this case alpha is greater than 1. Okay, so it slowly increases and keep on goes like this. So it is a growing exponential. Okay, when alpha is mod of alpha is less than 1, then it decreases like this. Fine. Now let us consider the third case. Now what we do is, we will assume that alpha is positive. Okay, if alpha is positive, then what will happen? C times alpha to the n, right? Let's say alpha equal to again 2, then whether you put n equal to 1 or 2 or minus 1, the value is always positive. So the above two cases are example of this one, right? Like let us assume c is equal to 1, alpha is equal to 2, then 2 to the n. If we substitute n equal to plus value, positive value or negative value, this is going to always yield a positive value. Like 2 power 1 2, 2 power 2 4, or 2 power minus 1 0.5, 2 power minus 2 0.25 and so on and so forth. But if you consider the other case, like case 4, where let me assume alpha is equal to, alpha is a negative value. Alpha is negative. In this case, what will happen? X of n will alternate its value between plus and minus. So let's say again c is equal to 1 and alpha is equal to minus 2. I am taking minus value. So in this case, your x of n is equal to minus 2 whole power n. When substitute n equal to 0, n is equal to 0, then x of 0 is equal to 1, then supply n equals, supply for n as 1, then x of 1 is equal to minus 2 whole power 1, that is minus 2, right? When n equals 2, then x of 2 equals minus 2 whole square, again plus 4. See, it is alternates between positive to negative and negative to positive. Here then 1 is positive and here 2 is negative, and again 4 is positive. The next value is going to be minus 8. So it is keep on alternating between plus value and minus value when alpha is negative. So in this case your sequence will be like this. When n equals 0, you'll get a positive value, let's say 1. When n equals 1, then you'll get a minus value, let's say minus 2. When n equals 3, then you'll get a when n equals 1, when this is 2, this value is 1 and this is 0, 1, and when n equals 2, you'll get plus 4 like this. When n equals 3, then you'll get minus 8 like this. So the values are alternating. Here it is positive value, negative value, positive value and negative value. So that depending on the value of alpha, if alpha is negative, then x of n alternates between positive value and negative value. So real valued discrete time exponentials are often used to describe population growth, as a function of generation, okay, and total return on investment. Investment as a function of day, month, year, or whatever it is. Okay, so that's all about real exponential signals. Let me show this, the last point, through a figure. Insert pictures. So where is it? It is alternating between plus value and a minus value. I don't know where it is. Yes, it is here. Here the values are like here alpha is negative and mod of alpha is less than 1. Okay, so that means the alpha lies between minus 1, less than alpha, less than 0. That's what its range is. And here alpha is greater than 0, mod of alpha, and alpha is negative. That means the alpha is less than minus 1. Sorry. Alpha is less than, yeah, it's right only. Alpha is minus 1, that's it. Minus 1, that's all. It's a growing exponential. It is growing like this. Okay. That's it. Now the next topic is sinusoidal signals. Sinusoidal discrete signals. So another important complex exponential is obtained by using this general form, x of n is equal to c times e to the j times, not j, e to the beta times n. Now what we do is we consider c is a complex value and assume mod of alpha is equal to 1. Okay, so that means what? Originally we started with x of n is equal to c times alpha to the n, and we replaced alpha is equal to e to the power of beta. So c times e to the beta n. So this is my complex exponential. Now what you do? You take beta is purely imaginary. Then only you will get a sinusoidal function, otherwise you will not get it. Recall from the previous lectures that when in the continuous time case, if the s values lies between on the j omega axis, then you'll get a cos omega naught t like this. Like let's say this is plus omega naught and this is minus omega naught. These two guys will combine and will give rise to cos omega naught t. Similarly, here I am considering beta has to be purely imaginary. Let's say beta is equal to j omega naught. Okay, so therefore this is going to be c times e to the j beta n. And for the time being, let us I'm sorry, j beta equal to j omega naught, right? So j times omega naught n. So this is my x of n. Now I will make one more assumption. Let us take mod of c is equal to 1. So or c, let us assume some number for that. Therefore e to the, because that scaling factor is not very important for us now, so e to the j omega naught n, and this is x of n. So this is a complex exponential. The real part is 0. Okay, here we assumed mod of alpha is equal to 1. That means what? E to the j omega naught n, if you take magnitude, it is equal to 1. Okay, so as I said, this complex number always comes with its friend. Who is his friend? Complex conjugate of this guy itself. So e to the minus j omega naught n. So as in the continuous time case, this signal also, this e to the minus j omega naught n, also closely related to the sinus, its counterpart. Okay, whose counterpart is this guy, e to the minus j omega naught n. If you add these two guys together, then e to the j omega naught n plus e to the minus j omega naught n, then it is going to be 2 times cos of omega naught n. So in general, the sinusoidal function is written as a times cos of omega naught n plus some initial phase phi. Okay, now this n is a number, so there is no unit for that, dimensionless quantity. Then omega naught and phi both are measured in radians. Okay, but in the continuous time case, if you remember, when I write cos omega naught t, then here this omega naught is measured in radians per second, but here it is only radians. If you write like this, cos omega naught t plus phi, and this phi is radians. So here this omega naught is not in radians per second, it is only in radians, and phi also in radians. So please remember this difference between the continuous time case and discrete time case. Okay, so this is a general form of sinusoidal signal, discrete time sinusoidal signal. Okay, by using Euler's relation, it allows us to relate complex exponentials and sinusoids. So e to the j theta, we know that cos theta plus j times sin theta. Similarly, we can write e to the j omega naught n is equal to cos omega naught n plus j times sin omega naught n. Similarly, if we have cos omega naught n plus some phase angle phi multiplied by a, as we did in the continuous time case, is equal to a by 2 e to the j phi, then e to the j omega naught n plus a over 2 e to the minus j phi, then e to the minus j omega naught n. Okay, so e to the j omega naught n and cos of omega naught n plus phi multiplied by some values. These two are examples of discrete time signals, okay, with the infinite total energy. With why is it infinite total energy? We also gave the reason for the continuous time case. For example, you take e to the j omega naught t, and if you take the magnitude, then it is going to be 1. Okay, so every sample of the signal, this e to the j omega naught n is going to contributes 1 to the signal's energy. So if you find the total energy for minus infinity to plus infinity, then the energy is going to be infinite if you find the total energy. Okay, while the average power, if you find out average power over infinite duration, over one period, average power, then average power per time point is obviously equal to 1. Okay, so therefore these two signals are power signals, not energy signals. Okay, so now let me show you some figures regarding this pictures. Then in this so this is a sinusoidal signal. Fine, and this is not readable, so x of n is equal to cos of 8 pi n divided by 12. You can substitute n equal to 0, then you find out value. Maybe let's say this is 0 and the corresponding value is this. You take your calculator, put it in the radian mode and substitute. When n equal to 1, then substitute n equal to 1 here. N is equal to 8 pi divided by 12, that is 2 times 8 and 3 times 4, 2 pi by 3 cos of 2 pi by 3. This point is cos of 2 pi by 3, and so on and so forth. You can keep on calculate. When n equals 3, then you find, so this is going to be n equals 3, and this is 4, you will get n equals 5, you will get like that. Okay, so this is a typical sinusoidal signal in discrete time. So let me show you one more figure. Pictures. Yeah. So this is cos of 2 pi n by 12. X of n is equal to cos of 2 pi n by 12. You substitute n equal to 0. Cos 0 is equal to 1. Therefore, this value may be 1. And then substitute n equals 2. Then n equals 1. Then 2 pi by 12, that is pi by 6, cos of pi by 6. So this is going to be cos of pi by 6. Like that you can find out all other values. This is 0, 1, 2, 3, 4, 5, 6, like this. So when n equals 3, it is 0. So let us check how it is 0. When n equals 3, then cos of 2 pi times 3 times divided by 12. So 2 times 3 is 6. So it is cos of pi by 2. Cos of pi by 2 is of course 0. It's correct. So this point represents 3, 4, 5, 6, 7, 8. Then again this point is 9. Then this point is 10, 11, 12, 13, 14, and this point is 15. You can substitute different values and you can find out the corresponding amplitudes. Even if you want, you can plot these figures. Take your calculator, supply the value for n and you will get the amplitude. Okay, now you will get more number of samples. One more example, insert pictures. Yes. And this one says x of n is equal to cos of n by 6. Okay. Now you put n equal to 1, 2, 3 and so on, and you'll get a plot like this. So these are the examples for discrete time sinusoidal signals. Now let me consider general complex exponential signals. Okay, so we said the complex exponential signal is written as c times alpha to the n. Okay, so this is the general form of general discrete time complex exponential, general form of complex exponential signal, and this signal can be written in the polar forms. Okay, so because c is complex and alpha also complex. Okay, so we can write these two complex numbers either in the polar form or rectangular form or magnitude form. There are many forms. Okay, so let us write in the polar form, and then we will try to interpret in terms of real exponentials and sinusoidal exponentials. Our aim is finally we need to get real exponentials and sinusoidal components. If the same thing we have done in the continuous time case also. What we did there, we had e to the st a bar like this. What is a bar? We have written a times e to the j phi, if you recall, and this is going to be sigma plus j omega times t. And as I said, this always comes with its pair, conjugate pair. So a to the minus j phi plus e to the sigma minus j omega t. Then if you combine these two guys, then it is 2a times e to the minus sigma t, then cos of omega t plus phi. This is what we got it there. So therefore we started with the complex exponentials and finally we obtained this result. And this one is real exponential, and this one is going to be a real sinusoidal signal. So we start with the complex exponential, but ultimately we will reach real exponential and real sinusoidal signals. That's what we are going to do now. So let us write the complex number c in polar form. So in the polar form, let me write mod of c times e to the j theta, its angle theta. Similarly, this alpha also let me write in the polar form, mod of alpha times e to the j omega naught in this form. Okay, so therefore c times alpha to the n is equal to mod of c times e to the j theta mod of alpha times e to the j omega naught. Okay, so j omega naught, n will come because there is n, no, so that n also will come here like this. Right, now you combine this different terms, then it is going to be mod of c times mod of alpha whole to the n times e to the j theta plus e to the j omega naught n. Now mod of c times mod of alpha times n, these two are real because you have taken magnitude, and this one you combine e to the j omega naught n plus theta. As I said, the exponential always occurs with its pair, conjugate pair. What is a conjugate pair? E to the minus of j times omega naught plus theta. It will never come alone. It always comes with his friend. Who is his friend? Complex conjugate of himself. Okay, if you add these two guys, then mod of c mod of alpha to the n, so within a bracket e to the j omega naught n plus theta plus e to the minus j omega naught n plus theta. Now divide by 2 and multiply by 2. So this is 2 times mod of c times mod of alpha times to the n cos of omega naught n plus some initial phase theta. Okay, so like this we can write. So this is the general form of sinusoidal signals. Okay, finally we'll arrive this. Now you take this guy, this one, like use your Euler's identity. E to the j theta is equal to cos theta plus j times sin theta. Therefore that is, this one is written as mod of c mod of alpha to the n cos of omega naught n plus theta plus j times sin of omega naught n plus theta. Take these two guys inside. So mod of c times mod of alpha times to the n cos of n omega naught n plus theta plus j times mod of c mod of alpha to the n sin of omega naught n plus theta. Okay, now let us assume alpha equal to 1. Then what will happen? If mod of alpha is equal to 1, then it is mod of c cos of omega naught n plus theta plus j times mod of alpha sin of omega naught n plus theta. Now on the left hand side you have mod of c e to the j omega naught n. Therefore the complex exponential has two sinusoidal. One is cos omega naught n plus theta and the other one is sin omega naught n plus theta. This cos omega naught n plus theta is nothing but the real part of e to the j omega naught n, and this one is nothing but imaginary part of e to the j omega naught n. Okay. Now let us consider two cases here. If mod of alpha is less than 1, then they correspond to sinusoidal sequences multiplied by a decaying exponential, because already we have seen that if mod of alpha to the n is less than 1, then what will happen? This sequence will decay like that. So therefore you are multiplying and multiplying a decaying exponential with a sinusoidal signal. So it starts from 1, then it keep on reduces like this, it goes like this, then you will have a sinusoidal sequences, sinusoidal or cosinusoidal. So if you multiply these two guys, then you will get decaying exponential. Similarly, if alpha is greater than 1, then you will get a growing exponential. Okay, so let me insert a figure, then you will get a better picture. I have a picture for this taken from the book. See, here I have the sinusoidal signals. The signal is going like this, increasing and again coming down, and again it is increasing like this. So this is my exponential real time like this, alpha to the n. This one is, this dotted line indicates that one, and this is my sinusoidal function, that is cos of omega naught n plus phi. This represents cos of omega naught n plus phi or theta, and this one represents alpha mod of alpha to the n, where mod of alpha is greater than 1. If mod of alpha is less than 1, then it is a decaying exponential. So let me show you the figure. Insert. So this is a decaying exponential. See, initially the magnitude is like this. The magnitude is like this, then slowly it is decreasing. So therefore it is decaying exponential if alpha is less than 1, mod of alpha is less than 1. So in this lecture we have discussed the discrete time, complex exponential and sinusoidal signals. Okay, so we looked at the general form of complex exponential signal or sequence. In discrete time signal we will also call discrete time sequence, and then we looked at real exponential signals, and then we looked at sinusoidal signals. Again, in the sinusoidal case we had two types. One is growing, in general form we had two types. One is growing sinusoidal signals, and another one is decaying sinusoidal signal. I mean decaying discrete time sinusoid and growing discrete time sinusoid. This is decaying discrete time sinusoid, and this one is growing discrete time sinusoidal signal. That's it. Okay, so let me stop at this point.